Hey grade 12s, so if electrostatics is a bit confusing or if it's been a while since we've last done it, we're about to work through question 8 of the June 2025 physics paper, so we can break down the structure of the paper, revise Coulomb's law, as well as electric field at a point and the relationship between the electrostatic force and the charge. So question 8 says 3 point charges A, B, and C are placed as shown in the diagram below. So we have A here with minus 5 times 10 to the negative 6 coulombs, B is positive 2 times 10 to the negative 6 coulombs, and then C over here is positive 7 times 10 to the negative 6 coulombs. Cool, we have the distance here between A and B, and we do not have the distance between A and C. So that is most likely going to be a question coming up. So then 8.1 says, state Coulomb's law in words. So what we have is this that we can help link the words to. So I'm just going to write it down so long. So this formula here, this is the electrostatic force. This is the charge of Q1, the charge of Q2, and the distance between them squared, always measured in meters. K over here is on our formula sheet. It is one of the constants that is given, and its value is 9,0 times 10 to the 9. So Coulomb's law is this guy first. It is the magnitude of the electrostatic force exerted by one point charge Q1 on another point charge Q2 is directly proportional to the product of the magnitude of the charges, the fact that these two charges are multiplying one another, and is inversely proportional to the square of the distance r between them. So that is Coulomb's law, and that is how we link it to the formula, seeing that we start with the magnitude of the electrostatic force over here exerted by one point charge on another point charge. 2 is over here, is directly proportional, is this 3 over here, to the product of the magnitude of the charges, and then 4 over here is inversely proportional to the square of the distance between them. So that just earned us 2 marks over there and is telling us that we are going to use this formula in the next question. So then 8.2 says the net force on charge A over here due to the charges B and C is 0.866 newtons. Okay, it says calculate the distance D as indicated in the sketch above. So we need to make this statement true, and over here they said the net force, which is very important, which means it isn't just this formula once. What we're doing is this formula twice because we have the net force over here. So we have to do this formula once for B on A, and then this formula again for C on A, and then equate them to the 0.866 newtons. So we'll set that up over here. And then only one other thing to keep in mind as we set this up is that these guys are not working in the same linear plane. It's not like C is over here and they're just playing a game of tug of war over A, for example. What is happening is that our resultant force is our hypotenuse over here, which means we're actually working with this in terms of Pythagoras. So our equation, we're setting it up very similarly to how we would if they were in a straight line, but we're just working with the fact that our F net is 0.866 over here for the hypotenuse, which means when we plug that in, we just have to use squared values because that is how we work with our Pythag formula. So what we have is F net squared equals FA on C squared plus FA on B squared, which means this is A on C over here and this is A on B over there. These are the two sides of our right angle triangle, and then our F net squared is our hypotenuse. Okay, so we have this set up here. We just need to write this formula in full because we get 1 mark for that. So we still have our F net squared, and then what we need to do is plug in these symbols here as far as K remains the same, and then for A and C we have QA over here, and then we have QC over there, and then this is over R squared, and then we're going to add the same thing. We have K here, we have our Q of A, and we have our Q of B, and then this is also over R squared. And then now that we have this and just earned 1 mark, we can go ahead and plug in our values over here. So our F net is 0.866 squared. Our K is what we have on our constant sheet, that is 9,0 times 10 to the 9. Our QA over here is -5, but we don't have to plug in the negative into these formulas, considering this negative is being attracted to this positive, this B over here, and this negative is also being attracted to this 7 over here, which means we can ignore it because they're both being attracted, and either way, considering we're going to square this whole formula here, it means we do not have to insert the negative there because ultimately it is going to end up positive. So when we plug in our QA, we can just plug it in as 5 times 10 to the negative 6. The negative 6 has to remain, but the negative in front of the 5, that can go away. Cool. And then our C value is 7 times 10 to the negative 6 over there. And then when we plug in our R in this case is D. That is the distance that we want. And then we must just remember to square that as well. Then we're going to do the same thing over here with this formula, plugging in our K value, our constant, and then our QA. We have that over here. That is our 5 times 10 to the negative 6, just as we did in this calculation. Cool. And then QB is 2 times 10 to the negative 6. So we can just sub that in. And then this is all over our R, our distance, our 0,5 over there. And it is measured in meters, so we do not have to do a conversion. And then we just have to square that. And then one thing we haven't done yet is putting the square over everything, because we are doing Pythag. And in this setup over here, we just earned another 3 marks, 1 mark over here, 1 mark over here, and another mark over here. So we've earned 4 marks for this 5-mark question, which means we just have to go ahead and solve for D, and then we will have our final answer. Cool. And then at this stage, it looks like we might be able to drop the squareds, but we can't do that. I explored that option, and that answer does not take us to the same answer that we have on the memo, which means we have to work with the squareds here. So we have to square all the values that are just numbers first, which means the 0,866 squared is 0,749956. And then what we can do is we can simplify this whole thing, considering they're just numbers here, and then take it over and subtract it on this side. So we are just left with this on the right side. So this whole thing simplified in our calculator is 0,1296. So I just plugged this all in my calculator with the square, and I took it over to subtract it from the 0,866 squared. So we have these two guys, this guy and this whole guy on the left side now of our equal to sign. And then on this side of our equal sign, we have 9,0 times 10 to the 9 multiplied by 5 times 10 to the negative 6 multiplied by 7 times 10 to the negative 6 over d squared to the power of 2. The whole bracket. So I'm just going to rewrite that for us quickly. Okay, so we can just go ahead and simplify the left side so long, and 0,749956 minus 0,1296 is 0,620,356. We don't round at this stage, we only round right at the end. And then on this right side over here, considering there's a variable that we have in here, that is the reason we couldn't drop the square initially. So what we have to do is multiply the top and then square it, and then the d squared, we're just going to multiply by 2. Considering any variables with the power of 2, we multiply. Okay, and all of those multiplied and then squared equals 0,099225. And then our d squared, that is also getting the square, becomes d to the power of 4. At this stage, we're almost done. All we have to do is take our d to the power of 4 up top. We're just cross multiplying. So that is now in our numerator on the left side, and then bringing our 0,620,356 down to the denominator on the right side. And we still have the 0,099225 left on the top right. So we can just go ahead, simplify this in our calculator, and the answer that we have here is 0,1599 and that equals d to the power of 4, which means our last move is taking the 4th root of both of these on our calculator, and our final answer for d is 0,63 meters. So that just earned us 5 marks over there. Okay, and then 8.3 over here says charge C is now removed. Okay, so this guy is gone. Point P is 0,2 meters to the right of charge B. So we have charge A, the same charge as we did here. Charge B remains, C is now gone, and now we are looking at point P to the right of both of these charges. So 8.3.1 says define electric field at a point. So electric field at a point, the definition works with this formula over here. So I'm just going to rewrite it for us, which means the electric field at a point. So it starts off with the words that they give us for the definition. So we have the electric field at a point is the electrostatic force. So it is, the equal sign here is the electrostatic force, the F over there, experienced per unit. So per means divide, positive charge placed at that point. Cool. And the fact that it is a positive charge, so charge is our Q over here. The positive helps us orient ourselves when we do question 8.3.3 because the P is a positive charge over here. It is a positive speck of dust, and that helps us relate as to whether the B is repelling it it or attracting it, and whether A is repelling it or attracting it when we do the magnitude of the net electric field. So that part is just important when it comes to another calculation, but this just earned us 2 marks, and that is how we link the words to this formula over here. And then 8.3.2, it says draw a labeled vector diagram of the electric field at point P as a result of charges A and B. So as we were just talking about, charge P over here is a positive speck of dust. It doesn't attract like these charges up here. It doesn't have an actual charge that it emits, but it is a positive speck of dust, which is helping us see how it relates to A and B. By that I mean A is a negative charge, right? So A is negative and P is a positive speck of dust, which means A is trying to attract P over here. So these two guys are attracting, but then over here B is positive and P is positive, which means B is repelling P over there. And the fact that B is a lot closer to P than A has the biggest impact, because our formula when we are looking at our electric field, I'll write it down quickly. Our formula when we're working with electric field has an R squared, and the fact that the R is squared means the distance has the biggest impact on the electric field at a point, more so than the charge. So the fact that P is being repelled by B quite significantly and A is only attracting P with less pull, our resultant vector diagram is something like this. So we have our E net there. It is the difference between B and A, considering B is repelling P with more of an impact and A is attracting P with less of an impact, which means our E net is going slightly to the right, and that is our final answer there for 2 marks. And a nice way to think about it is imagining that P is a ball floating in a pool and B over here is splashing water away so that P repels, and then A is trying to paddle water towards it to try and bring P towards A. So that is just a nice analogy that works for some of my students to help us visualize this a bit better. The fact that B is splashing water away from P, therefore repelling it, and A is trying to paddle water towards it to bring the tennis ball P towards it. But considering it is further away, it is harder for it to paddle water towards it in order to actually affect P. So then we have 8.3.2. We're now on 8.3.3, and 8.3.3 says calculate the magnitude, the amount of the net electric field. So our E over here. So we focus on electric for the E. Our force is our F over there. So the net electric field, net as well, at point P. Cool. So this is 4 marks, and we're going to write the formula that we're working with. Okay, so we have our E net, considering they said the net electric field, and that is what we drew over here, considering they are minusing each other. 8.3.2 helped us see we are subtracting the electric field of A on P from the electric field of B on P. So this vector diagram helped us see that, and what we can't do is try and equate them on one equation. We can't put Q1 and Q2 on the same equation like our force over there. We have to treat it separately by writing KQ over R squared. This will be our QB on point P. The fact that it is 0.2 meters, we have to treat that separately. So this is equation 1, and A on P is equation 2, which means we are subtracting that from this guy. So we're going to write this here. We have our K. It is the same constant that we had in our previous question for 8.2. And then our Q over here is our QA, and that is over R squared. That distance over there is the 0.5 meters plus the 0.2 meters. The fact that the R is given, R in meters, is good for us, considering the R's here in this section are always measured in meters. So we don't have to do any conversions. And then also the fact that we have a minus here, it means when we plug our QA in, we do not have to plug in the negative there as well. We don't want to double up. What we want to do is put the minus outside and then just put the actual value for it, ignoring the negative in front of the 5. So our E net is what we want. Our K on our constant sheet is 9,0 times 10 to the 9. Our Q of B is 2 times 10 to the negative 6. And our distance between them is 0.2 meters squared. And then we're subtracting. K again is 9 times 10 to the 9 over there. Our QA is just 5 times 10 to the negative 6 over here. Cool. And we do not have to put the negative, otherwise we're going to double up our negative in front that we've already dealt with. And then that is over R squared, and that is 0.5 plus 0.2, which is 0.7 squared. So at this stage, we just earned 1 mark for this setup of the equation, and then another 2 marks for plugging in here correctly and plugging in here correctly. Our 4th mark would just be to put all of this in our calculator and get our final answer for our E net, which means I'm just going to go ahead and do that on my end, and our final answer for our E net is 358,163,27. Cool, quite a large number. And then our units are n.c to the -1. Relating back to our initial formula where we got the definition, where we have F over Q, which is newtons over coulombs. So this is our final answer here for 8.3.3, earning us 4 marks. And then 8.3.4 over here is a theory question. It says if point P, this point over here, was between charges A and B, so if point P was between charges A and B, the net electric field would never be equal to 0 at any point. Explain the validity of this statement. So is it true or false? That is 1 mark, and then why is the second mark. So P is a positive charge over here, and what happens is this negative is attracting this positive point charge to the left, and this positive is repelling this positive point charge that way, which means that no matter what, whether it is right in the middle or a little bit here or a little bit there, these two guys are on the same tug of war team, the same team as far as pulling the water towards it to bring the ball towards it, and splashing the water away from it to move the ball away from it. These guys aren't fighting for it. They're not fighting in opposite directions that can equate to 0. They are working on the same team in the same direction, which means that regardless of where it is put in between A and B, it can never amount to 0 because they are working in the same direction. So is this statement true or false? This statement is true because it would never be equal to 0. So we have true because the E net is always added, EA plus EB, and these two charges are working in the same direction. So 1 mark for true, 1 mark for our explanation, and that just earned us 2 marks. And then 8.4 over here, it says the relationship between the electrostatic force and a charge is illustrated in the graph below. During this experiment, the second charge and the distance between the two charges are kept constant. So we could ignore the second charge and we can ignore the distance. So we have the electrostatic force charge graph. We have our electrostatic force on our y-axis. That is our dependent variable. We have our charge times 10 to the -6 coulombs. So we have our microcoulombs over there. On our x-axis, that is our independent variable. And what we can see is that it is a perfectly straight line. So then 8.4.1 says, what mathematical relationship between the electrostatic force and the charge can be deduced from the graph? So it is only 1 mark, and it is talking about the fact that it is going from 0 all the way up in a perfectly straight line, which means it is just a directly proportional relationship. And that would earn us 1 mark over there, just saying directly proportional. And then last question for this section, 8.4.2 says, use the information in the graph to calculate the magnitude of the electric field, the E, around the charge when it experiences a force of 0,005 newtons. So 0,005 is over there and 0,005 is over there. This is 3 marks, and we are getting the electric field. So we're just going to rewrite this formula here. E equals F over Q. We don't have to work with E equals KQ over R squared because the other charge is kept constant and they are kept an equal distance away from each other, which means we can ignore this formula and just write this formula over here. So we have E equals F over Q. So that is option 1, or we can do a gradient formula because as we'll see, our gradient formula is exactly the same. Our change in Y is our electrostatic force here, taking it from there down to 0. And our change in X over here is the same thing, taking our charge from that point all the way down to 0. So our gradient formula, whenever it comes to graph questions, will usually be the exact same as our formulas, which means we can choose either option over here, but we can just work with option 1, plugging in our F and our Q based on the graph. So 0,005 newtons is what we're working with for our force, and then our charge over there is 1 times by 10 to the -6. Just don't forget the 10 to the -6 over there. So we can write that in, and our final answer is 5,000 newtons per coulomb to the -1. And that just earned us 3 marks for the last question and 21 marks for the whole section. Great job, guys. Let me know if there are any questions in the comments below, and otherwise I will see you in the next video.